So in this problem, we're going to look at an absolute value inequality application problem that deals with polling variance or voter variance when you're estimating who's going to win an election. So the problem says, suppose that polling data during a presidential election indicates that a particular candidate will receive 46% of the vote, and the poll indicates it has a 3% margin of error. What percent of the voters are likely to vote for the candidate if the polling data is accurate? And the idea here is when you're told on TV that a candidate seems to have a certain percentage of the vote, these are determined by taking random samples from the voting population and coming up with what is an estimate. And that estimate always has a margin of error. So we're given the estimate. We're estimating that we have a candidate who's going to receive 46% of the vote. And again, because this section has been on absolute value inequalities, the spirit of the problem is that you need to set up an absolute value inequality even if there are other ways to solve the problem. So we want to construct from this information an absolute value inequality that models the situation that we're in. So we have an estimate of 6%. There's a margin of error of 3%. And there's going to be an actual percent of voters who vote for the candidate. We don't know what that is, so I'll represent it with P. So P is actual percent received, right? We have an estimate, I before E, except after C, received. We have an estimate for how what percent of the vote we think someone's going to get, but on voting day, it's going to turn out some way that may not be 46%. So if the polling data is accurate, what we know is that the actual percent earned by this candidate minus the predicted percentage of the vote that they're going to receive, that this difference, the absolute value of this difference, if it's a 3% margin of error, should be less than or equal to 3%. The difference between what they earn and what they're predicted to earn, the absolute value of that to get rid of negative percents, should be within 3%. So we set up the absolute value inequality because that's the spirit of the problem. I probably don't need to put the percent symbol on there if I don't want to. It doesn't hurt to do it. When I get to the end, I want to make sure I understand I'm working with percents. And what we want to do is recognize that we have a less than or equal to symbol. So we have the absolute value of our algebraic expression less than or equal to 3. So we're in the classic AND situation where the 3... maybe I do want to keep the percent symbols on there. I kind of like it. Where the opposite of 3% is going to form one bound, and the 3% is going to form the other bound, and the algebraic expression is going to be sitting in between those two bounds, separated by the by the inequality symbol that we're working with, which is the less than or equal to symbol. So once I have set up the 3-part inequality, I now solve it the way that we've already learned how to solve these things. We're going to add 46% to all 3 sections of the 3-part inequality in order to get that P by itself. So when we add 46% plus minus 3%, we're going to get a 43%. Which is less than or equal to the actual percentage that the candidate is going to earn, is less than or equal to, bringing down this inequality. Add the 46% to the 3%, we'll get 49%. So the actual percentage earned, if the 3% margin of error is correct, should run between 43 and 49%. As a complete sentence, we would say something like this. The actual percent of the vote earned should be between, right? The percent earned is between two bounding numbers, should be between 43% and 49%, and because of the equal to sign, again, we're going to say comma inclusive. So we're including those boundary numbers of 43 and 49 as possibilities.